opposition of the current. It is the measure of opposition of the current. Fine. So it is represented by R. Resistance is represented by R. So what is the relationship here? R is directly proportional to the length of the conductor anbodu. Yes, R is here. I'll write it. R is directly proportional to the length of the conductor. R is inversely proportional to the area of cross section. Ohm's law alli maatadtirbekadre we get this resistance R. Howda? So there we have seen. So R is directly proportional to length, inversely proportional to A. Both the equations bitu, if you write, you will write it as remove the proportionality sign, introduce a constant, and the constant is rho L by A. This is my resistance, and the constant rho is called what? It is called resistivity. It is called resistivity. Similarly, if I talk about conductance, conductance is what? It is reciprocal of resistance. It is reciprocal of resistance. So I can say conductance as reciprocal of resistance. Andre, resistance is rho L by A. Conductance is 1 by rho A by L. Is that right? So 1 by rho A by L. This is conductance. So here you can see Ohm's law in the strength of the current is potential difference between any 2 points in a current carrying conductor is directly proportional to the current being passed through it. Correct? So remove the proportionality sign. You write V is equal to IR. So where R is resistance. And this rho, what you're seeing here, is called what? It is resistivity. So resistivity of a conductor is its resistance when the length of the conductor is 1 centimeter, having area of cross section 1 cc. Yes. So resistivity na I've shown here. It is L by A, or rho is equal to what? R into A by L. Yes. Unit of resistivity is ohm centimeter. Unit of resistance R is equal to V by R anta baritivi. Resistance the unit enu? The unit of resistance is ohm, which is symbolized like this, ohm. Howda? So resistivity the unit enu? Along with the resistance, this is also there. This factor is also there. So unit of resistivity is ohm meter. It is ohm meter. Fine. Okay. So conductivity is what now? Conductivity, it is defined as conductance of a solution placed between two electrodes of 1 centimeter apart and having 1 cc as area of cross section. 1 cc as area of cross section. So I can write here, you can see here also. So what does this conductivity definition tells me? What does it say? See, it is telling me that it is the conductance of the solution. L placed conductance solution L placed there. See this, can you see this particular tube what you are seeing here? This tube, glass tube, let me say this is my solution holding container anta ankolona. There is a solution and these are the two electrodes which are being placed. And the solution is between these two electrodes. Fine. And so this will be the length. Distance between the two electrodes is my length, and the area of cross section of this tube will be the area of cross section. Correct? So I can write, I know that conductance G is equal to what? 1 by R. Is that right? So what will be the unit of conductance? Unit of conductance 1 by R, reciprocal of resistance. So that the unit no reciprocal todi. Unit is ohm antandvi. So here the unit is mo. And the symbol is also inversed. Yes. So alternative unit of conductivity is Siemens, written as capital S. So mathematically, if you see, G is equal to 1 by R anta baritivi. That is nothing but 1 by rho. Just now I told you here into A by L. This particular constant 1 by rho here is denoted by the symbol K. It is denoted by the symbol K. What is this K called in terms of conductance? It is called kappa. It is called kappa. Okay, fine. So with this basic understanding, let us proceed further. So based on the conductivity of the solutions, based on the conductivity of the substances, the substances are classified into 3 types. So which are those 3 types? The 3 types are conductors, insulators, and semiconductors. So yadar mel basis, so it is based on the conductivity of the substance. Based on the conductivity, they are being classified into 3 types. So the 3 types are, so let me write here, conductors, then I have insulators, and semiconductors. Semiconductors. So what are conductors? So conductors are those with very high conductivity. G is very high. Insulators are those with very low conductivity or no conductivity andru nadiyutte. What are semiconductors? Semiconductors are those whose conductivity value lies between conductors and insulators. Their G value is between the range of conductors then range ಇದೆಯಲ್ಲ ಅದ್ರದ್ದು ಮತ್ತು ಇನ್ಸುಲೇಟರ್ಸ್ G value and range ಇದೆ. In between that lie the semiconductors. So conductors examples ಏನ್ ಅನ್ಬೋದು ನಾವು? We can give metals. So I have here metallic conductors. What do I have here? I have here metallic conductors. Insulators ಬಂದ್ಬಿಟ್ಟು all the glass, all can be taken. Ceramics ತಗೊಳ್ರಿ, these are all insulators. Semiconductors, silicon, all your metalloids. Semi-metals antivala, silicon, germanium, all these are what? These are what? Insulators. Fine. Okay. Now we'll try to understand in detail about how conductance happens in metals. That is, we will talk about metallic conductors. So metallic conductors andaga, conductance in metals, whatever electricity we study, we see in our day-to-day life is all because of this metallic wiring idella. Fine. Yes, and that you have studied to some extent in physics also. So metals have charge carriers. Metals possess charge carriers. And who are those charge carriers? Who are the charge carriers in metals? See, you know that these charge carriers are nothing but they are valence electrons. Who are the charge carriers? They are valence electrons. Valence electrons antandrenu? I need not repeat it again and again. The electrons which are present in the valence shell, in the outermost shell, they are called valence electrons. So these valence electrons being more reactive, since they are held very far from the nucleus, nuclear attraction ಸ್ವಲ್ಪ ಕಡಿಮೆ ಇರೋದ್ರಿಂದ, they are very free. So they can run from here and there. They can move from here and there. And then when they move into the certain piece of metal ಅನ್ಕೊಳ್ರಿ, ನಮ್ಮ metal wire ಅನ್ಕೊಳ್ರಿ, they start flow of electrons ಆಗತ್ತ. Flow of electrons ಅಂದ್ರೆ ಏನು? They are negatively charged species. So flow of electrons, flow of negative charges leads to what? It leads to current. Therefore I say in the metallic conductors, who are the charge carriers? Valence electrons are the charge carriers. Fine. So valence electrons play a key role in metallic conductors anta ಅನ್ಬೋದು. Yes. Flow of electrons contribute to what? Flow of electrons, as we said, it contributes to electric current. So metallic conductance, on what basis it depends? What are the factors for metallic conductance to be very good? So metallic conductance, first point, it depends on the nature of the metal. Obviously, nature of the metal. As metallic nature increases, conductivity will be more. As metallic nature decreases, conductivity will be quite less. Howda? No, it is not like that. So nature of the metal, what type of metal you have taken. Do you know which is a very best conductor of electricity? That is silver. Silver you have, copper you have, yes, and so on, iron you have. Correct? Fine. Then second, it depends on the structure of the metal. Structure of the metal. And lastly, number of electrons per atom. Number of electrons per atom. So it depends on these 3 important properties. So metallic conductance decreases with increase in temperature. This is another property. What? Metallic conductance decreases with increase in temperature. As you increase the temperature, metallic conductance ಏನಾಗುತ್ತೆ ಹೇಳ್ರಿ? Metallic conductance decrease ಆಗುತ್ತ. There is decrease in the metallic conductance. Now why is it so? Let us try to understand. Yes. Now see, what is the condition inside the metal? The valence electrons inside the metal are moving. So if I want to show here, let me say this is my metal piece. So there are atoms. Yes, atoms are present. So, and the electrons, shells idava. Valence electrons and the electrons in the outermost shell, correct? Electrons in the outermost shell. Electrons in the outermost shell. So these electrons, since they are less tightly held by the nucleus, they will be moving. So they will be moving. So let me say they'll be moving like this. Correct. So flow of movement of electrons will be like this. Right? Fine. Yes. Okay. So think of the valence electrons and their movement. The atoms movements are haphazard. See, okay, what is happening here? So if I increase the temperature, atoms are set there. Atoms only set agida. You know that metallic conductors and we talk about solids. Solids only closely packed structures. The molecules are atoms are held strongly. Therefore, atom movement illa. But flow of electrons is there. It is in a particular direction. Therefore, there is flow of electrons and the charge is there. Fine. Now my question is, when I increase the temperature, what happens? Please think over it. The atoms on heating themselves start moving. Illi electron movement aiti. Okay. But on heating, they themselves start moving. These atoms themselves start moving. The movement of these atoms, you just imagine the movement of valence electrons and the movement of atoms. The atoms movements are in a very zigzag manner, haphazard manner. So the electrons get struck up. Atoms se move aga to electrons do not understand how to move and what happens. So basically electrons get struck up there. So basically direction of the flow gets restricted. Flow electrons in the direction of flow gets restricted. So ali flow ne restrict aitantandre, if a flow of electrons gets restricted, if flow of electrons get restricted, tell me, will there be any current? There will be no current. Or I can say instead of no current, current will decrease because flow of electrons is restricting. How then? Therefore, we say metallic conductance decreases with increase in temperature. Fine. Now let's talk about the second type of conductance, that is electrolytic conductance. Electrolytic conductance. Okay. So electrolytic conductance means what? Conductance of electricity by whom now? Metallic conductance, conductance of electricity by metals. Electrolytic conductance, conductance of electricity by electrolyte. Is it by electrolyte actually? Not actually. By the ions present in the electrolyte. Conductance of electricity by the ions present in the electrolyte only, or present in the solution only, because only in solution they are dissociated into ions. Getting my point? So conductance of electricity by the ions present in the solution is called electrolytic conduction, ಅಥವಾ ನೀವು ಅದಕ್ಕೆ ionic conduction nu ಅನ್ಬೋದು. Because who are the charge carriers here? Who are the charge carriers? Here, unlike metallic conductors electrons were the charge carriers. Valence electrons were the charge carriers, right? But in electrolytic conductance, ions are the charge carriers. Ions are the charge carriers. So to understand this, let us take a very simple example of water. See, water dissociates as, how it dissociates? It dissociates as H plus and OH minus ions. So H plus and OH minus ions are present in the solution and its conductivity is very low. Means on its own, it will pass very less current anta artha. Conductivity low aitantandre eno, on its own it will pass less current. Okay, fine. Now, but if you add an electrolyte to this, electrolyte andre any salt, let me say I will add NaCl. Yes, I will add NaCl. So if you add NaCl, what happens? NaCl heng dissociate agutte? It dissociates as Na plus and Cl minus. So these Na plus and Cl minus ions get into the solution. they get into the solution. And we can see conductivity will increase. In fact, you can see it through the experiment. Even experiment nodabodu. You make a circuit, you just think of it. Make a circuit. Circuit ಒಳಗೆ ಏನೇನು ಯೂಸ್ ಮಾಡ್ತೀರಿ? You will use a beaker in which you have taken water, connected to the, see the bulb connections ಎಲ್ಲ proper ಆಗಿ ಮಾಡಿ, take a bulb, see immersing the two metal rods in water, see the bulb glows, the bulb will be glowing. Now what you do, because H plus and OH minus, they'll not carry that much current, and just now we have seen. Slowly you take a spoon of NaCl and add to it and keep on stirring. Observe the bulb. ಯಾವ ಬಲ್ಬ್ ಮೊದಲೇ ಫೇಂಟ್ ಆಗಿ ಗ್ಲೋ ಆಗಕತ್ತಿತ್ತು, on adding NaCl and stirring it, it starts glowing much brighter. It starts glowing much brighter. So by this experiment, or you can say intensity of the bulb increases. Intensity of the bulb increases. So it will increase means salt along with water increases the conductivity. Sumne bare NaCl tagondre solid NaCl will not do anything. Solid NaCl ಅಲ್ಲಿ, because Na plus and Cl minus dissociate agudilla solid ಅಲ್ಲಿ. NaCl ಬೇಕಪ್ಪ, you have to either take it in aqueous form, solution form ಅಲ್ಲಿ ತಗೊಳ್ಬೇಕು, or you have to take it in molten state. Because only in these two cases, NaCl dissociates into Na plus and Cl minus. So salt along with water, it will increase what? Will increase the conductivity. Electricity is being increased. Conductivity flow of electricity is more. Same thing was said by Faraday. That is, some substances in their aqueous solutions conduct electricity. And the substances which conduct electricity are called electrolytes. What are they called? They are called electrolytes. Yes. So electrolytes are nothing but they are salts. Salt is an example of electrolyte. All salts are electrolytes. Okay. So they conduct in their aqueous solution. So rather than saying salt, I'll say salt solution. So substances in their aqueous solutions, when conduct electricity, such substances are called electrolytes. Now the question is factors on which the electrolytic conductance depends. Metallic conductance we have seen. So it depends on, the first factor is, it depends on the nature of the electrolyte. Nature of the electrolyte. What type of, we'll see this in detail. What type of electrolyte you have taken. Second case, it depends on the nature of the solvent. Water, what solvent you have taken, that is also has to be seen. Third, it depends on the size of the ions. Then it depends on solvation. How easily the ions get dissociated of ions, means how easily can these ions dissolve in water, solvation antivadu. Then it depends on the concentration of electrolyte. So only 1 spoon salt haki, see how much bulb glows, and then you add 2 spoons, then you add 3 spoons, the bulb intensity of the brightness of the bulb will be more. And last one is temperature. Last one is temperature. So on all these factors, my electrolytic conductance depends. Okay, fine. So here electrolytic conductance, so conductivity, the unit of conductivity K is what? Unit of conductivity K is kappa. Okay, which can be also written as 1 Simon per meter square. Different materials have different conductivity values. Conductance of a solution increases on dilution, that is by adding water, but its conductivity decreases as the number of ions per unit volume decreases on dilution. Okay, so before going to this particular point, molar conductivity, let us talk about electrolytes. Fine. Okay. Yes. Okay. So you can see here, what question arises as soon as we use the term electrolyte or conductivity is how to measure the conductivity of this ionic solution. Electrolytic solution kottidar namga, adar conductivity heng measure madodu. How to measure the conductivity of the electrolytic solution. Here yakappa, why it becomes difficult to measure? Because see, we have two problems here. We have two problems. First is we are dealing with the solutions. We are dealing with what? We are dealing with solutions. So solutions in direct wires habitu passing the direct current. Can we solution itself get solution? The composition change if you pass DC current. So here instead of DC, what we can do? We can use AC, that is alternating current. Alternating current can be used. Okay, fine. So this problem gets solved. Second problem is, since we are dealing with the solution using wires, and how to make the circuit heg madodu? That is the important question. So here we use a specially designed vessel. That specially designed vessel is called conductivity cell. Like in electrochemical series, we have seen electrochemical cell, right? So here we have conductivity cell, and that was what we were seeing here, the conductivity cell. So this is the conductivity cell, and there are different conductivity cells also. So let us take one by one. So conductivity cell in detail agi now nodbekandre, this is the setup. So what is happening in the conductivity cell? We insert two platinum electrodes which are coated with platinum black. We arrange both the electrodes in such a way that you can see here, we arrange both the electrodes in such a way that between the distance between the two electrodes is called this distance. Can you see here? This particular distance, I'll take it like this. So this particular distance, the distance between the two electrodes, the distance between the two electrodes is taken as L. This distance is taken as L. Okay. Then this will be the glass rod in the glass tube. This is nothing but what? This is the area of cross section, which is denoted as A. So if I want to find conductivity bekappa, let us find the resistance. Resistance ಕಂಡುಹಿಡಿದ್ವಿಯಪ್ಪ ಅಂತಂದ್ರೆ conductivity ತಂತಾನೆ ಆಗಿ ಸಿಕ್ಬಿಡುತ್ತೆ. Yes, because what is resistance? Resistance is 1 by kappa. Correct? So in case of resistance, we write it as A by L, L by A. But in case of conductance, how do we write it? We write it L by A. Just now we have seen. Nodidvela. So I'll tell you once again. Rho into L by A. That can be written as kappa. So 1 by rho A by L agata. So that is 1 by rho is what? Kappa into A by L. This particular thing, what you are seeing, A by L, kappa is called, K is called conductivity constant, that is conductivity. A by L, what you are seeing, is called cell constant. A by L is called cell constant. It is called cell constant. Fine. So applying the constant here to this particular, wires are left here. Applying the constant concept of Wheaton's bridge, physics lo kaltidiri, we can find the resistance of this. So in fact, from this we can find conductivity also, because ಒಮ್ಮೆ ನಮಗೆ resistance ಸಿಕ್ತು, 1 by resistance is my conductivity. So here what is Wheaton's bridge? Tell me. Wheaton's bridge is nothing but R1 by R2 is equal to R3 by R4. This is the Wheaton's equation anta anbodu. Yes. So if you know this, if you know resistance, once I know the resistance, conductivity is not a problem. Okay. So now we have found conductivity of ionic solutions anta ankodu. Okay. So we have found the conductivity of ionic solutions. Fine. Okay. To make it more effective, let us introduce the term called molar conductance athwa molar conductivity. So when I say molar conductivity, the first question which arises to my mind is conductance. Why I need to study molar conductance? Conductivity aitalappa saku. Why I want molar conductance? Yes, getting my point. So conductance of a solution of different electrolytes in the same solvent and at a given temperature, it differs. Solution the conductance in aitala, if you take different electrolytes, ಒಂದೇ solvent ಅಲ್ಲಿ ಬೇರೆ ಬೇರೆ electrolytes ತಗೊಂಡಾಗ, the at a given temperature, because temperature in the vary agtati, factors we have seen, it differs, the conductance differs. Why it differs? It is because of charge and size of the ions. Okay, even because of the concentration and both. And with what is kinetics of the reaction, with what is the reaction is going to carry out. Fine. So because of all these things, we were noticing that even though for a particular solvent at a particular temperature, if we were seeing conductivity, it was different for different solvents. So molar conductivity will be a good idea. Molar conductivity, right? So molar conductivity is it is denoted by delta M. Lambda M. It is denoted as lambda M. This lambda, see, teacher, we have seen lambda, symbol for lambda is this, right? This is small letter lambda. Here in lambda also we have capital and small letter. So this is my capital letter lambda. Lambda M stands for what? Lambda M stands for molar conductance. It stands for molar conductance. So come on, let us try to understand this now. Molar conductance antandre enu? Something related to concentration, correct? Fine. So I'll write here molar conductance. Denoted by lambda M. Fine. So let us understand the mathematical aspect of this molar conductance. See, we know that resistance R is equal to rho into L by A. That is equal to 1 by G. That is conductance. So how I'll write 1 by lambda, 1 by rho into, or let me make it like this, 1 by kappa into L by A. So rho is nothing but 1 by kappa. L by L, write it as it is. So kappa is what? Kappa is my conductivity. Let's talk about normal conductivity. So K is equal to L by R into A. Correct? So 1 by R is what? I can write this also as 1 by R L by A. Now this L by A, the length between the electrodes and the area of cross section remains constant, and that is what? That is my G. That is cell constant. G star, cell constant. Yes. Okay. So I can write it as kappa is equal to cell constant by R. So this is what? This is normal conductance. This is my normal conductance. Now let's talk about molar conductivity, which is denoted by lambda M. See, molar conductivity, how do we define it? It is the conductivity per unit concentration. It is the conductivity per unit concentration. So I can write lambda M is conductivity andaga kappa, per unit concentration is by C. Yes, conductance andre enu? It means that molar conductivity is conductivity per unit concentration. What does that mean? It means that it is the conductance of, for 1 molar solution. It is the conductance for 1 molar solution. Is that right? So what will be the unit for kappa? As we said, it is Simon meter inverse. Meter inverse. What is the unit for concentration? Concentration, mole per meter cube. Yes, mole per meter cube. Is that right? So many a times in the questions, this concentration term is indirectly given. Let us say concentration molarity comes into picture. And what's molarity? Molarity is moles per liter. But here we have cubic meters per cubic meter. So you have to be very careful during the conversions. Conversions time ಅಲ್ಲಿ ನಾವು ಬಹಳ ಕೇರ್ಫುಲ್ ಆಗಿರಬೇಕಾಗುತ್ತಾ, because here moles per liter ಅಂತೀವಿ ನಾವು molarity, but here unit given is moles per cubic meter. ಹೌದಾ? So ಅದು conversion factor ಬರುತ್ತಲ್ಲಿ. Conversion factor is what? Conversion factor is 1000. So that can be written as, so see, 1 mole per cubic meter in terms of molarity can be written as molarity into 1000 liters, right? Molarity into 1000 liters. Yes, fine, cleared with this. So this is the molar conductance. Now here we are going to discuss. So let us see what is given in our synopsis. The conductivity of all ions produced when 1 mole of an electrolyte is dissolved in VmL of solution is known as molar conductivity. It is the conductance of 1 mole of an electrolyte placed between two electrodes 1 centimeter apart, length is 1 centimeter, having the area of cross section V centimeter square. So it is related to conductance. Just now we have seen lambda m is equal to 1000 conversion factor into kappa by m. What is m? Molarity. What is m? Molarity of the solution. Its units are per ohm, centimeter square per mole, or Simon meter square per mole. This is the SI unit. The SI unit for molar conductivity is Simon meter square per mole, and its conversion factor is given here. Conversion factors yak bekagat hedri during solving the numericals we need the conversion factor. Okay, fine. So here you can see all the things are being given. So lambda m, we know that conductance of a solution is 1 cc is G, and conductance of 1 mole of VCC solution is VK. VK, which is the definition of molar conductance. You just noted it. Okay. So molar conductance is V into kappa. Fine. V into kappa andre 1000 by m. Yes. So let the concentration of the solution be m molar. So m moles of electrolytes are dissolved in 1 liter. 1 liter andre 1000 cc of the solution. Hence 1 mole of electrolyte dissolved in 1000 by m cc of the solution is equal to what? VCC. So I can write it like this here. Or molar conductivity is equal to 1000 K by M. This was what we have seen in the previous slide. What are the units of molar conductivity? The units of molar conductivity is Simon per meter bar. Simon per meter kappa unit adu. Fine. Bar moles per liter. Molarity unit to. That is equal to Simon per meter by moles per cubic meters. Yes. So you numerical solve madbekadre we want all the factors into 10 raised to 3000. So SI unit of molar conductivity is Simon meter square per mole. With the increase of temperature, G conductance, K conductivity, and molar conductivity all increases. With the decrease of temperature, with the decrease in the concentration on dilution, G increases, conductance ಹೆಚ್ಚಿಗೆ ಆಗುತ್ತಾ, because dilution ಮಾಡಿದಾಗ ಏನು, we'll see it one by one. Dilution ಮಾಡಿದಾಗ ಏನಾಗ್ತದೆ, that's what we are going to discuss in our next point. Dilution ಮಾಡಿದಾಗ ions, they are more in number. K decreases, conductivity decreases. ಯಾಕಂದ್ರೆ concentration ಕಡಿಮೆ ಆಗುತ್ತಾ, but molar conductance, it will increase. Now this particular point we are going to see. Okay, so how this conductivity varies with molar conductance is what we are going to talk now. How the conductivity varies with molar conductance. Fine. Okay, so let's get started with that. Okay, so how conductivity varies with molar conductivity. Okay, yes, fine. So see, we'll be discussing two things. One, variation of conductivity, that is kappa, and the second, variation of molar conductivity, that is lambda m. And very interesting is, we will see whether weak electrolyte or strong electrolyte, whether you are talking about weak electrolyte or strong electrolyte, as the concentration is increasing, kappa, meaning what? Conductivity increases. For a weak electrolyte or a strong electrolyte, as concentration increases, conductivity also increases. Yes, but this conductivity decreases with decrease in concentration both for weak electrolyte and strong electrolytes. But when I speak about molar conductivity as concentration decreases, molar conductivity increases. Molar conductivity increases with decrease in concentration. Vice versa. Okay. So the question that arises in your mind is, students, if I see variation of conductivity and molar conductivity, kappa and lambda m, with the concentration, it is exactly opposite. For conductivity, as concentration is increasing, conductivity is also increasing. As concentration is decreasing, conductivity also decreasing. But for molar conductivity, as you increase the concentration, conductivity is decreasing. As you decrease the concentration, conductivity is increasing. So this is what? This is exactly opposite to each other. This is exactly opposite. Yes. So first, to understand all this, first we will see variation of a conductivity with the concentration. How K varies along with the concentration. So relative relation between these two we will understand. K antandrenu kappa, that is conductivity. Kappa is directly proportional to concentration. That is, increase the concentration, kappa increases, decrease the concentration, kappa decreases. And this is true for both strong and weak electrolytes. Fine. Now, what we will see, why it happens. Why when you increase the concentration, the conductivity increases, or when you decrease the concentration, why the conductivity decreases. When I say concentration is increasing, whose concentration I'm talking about? Means it is the concentration of ions in the solution which is increasing, correct? So let us suppose say that I have put salt in water. That means I have a salt solution. If I go on putting salt in it, it becomes concentrated solution, you say, right? What does that mean? What does that mean? There are more number of ions. It means that solution contains Na plus and Cl minus. Those number of ions are more, which means I have more number of current carriers, correct? So solution you concentrate ಮಾಡ್ಕೊಂತ ಹೊಂಟಿರಿ ಅಂದ್ರೆ more number of H plus ions are there, more number of ions are there. When there are more ions, they are current carriers. In case of electrolytic or ionic conductance, more ions contribute to more flow of current. So more flow of current means what? More ions contribute to more flow of current. So current flow ಜಾಸ್ತಿ ಐತಿ ಅಂತಂದ್ರೆ ಅದ್ರದ್ದು ಅರ್ಥ ಏನು? More flow of current means conductivity is more. Conductivity is more ಅಂದ್ರೆ ಏನು? Kappa is more. Is that right? Getting? So obviously my conductivity will increase. This is the simple logic. Less concentration ಅಂದಾಗ ಏನಾಗುತ್ತೆ ಹೇಳಿ? Concentration ಕಡಿಮೆ ಐತಿ, you are diluting. Yes. So conductivity is dependent on what? It is dependent on the number of ions per unit volume. Conductivity depends on number of ions per unit volume. How many ions are there in a particular volume? How many ions are there which will carry current? Getting my point? So number of ions per unit volume. On this particular point, the conductivity depends. So if you are going on increasing the concentration, number of ions will increase. Number of ions is increasing. Under concentration ಹೆಚ್ಚಿಗೆ ಆಗಕತ್ತೈತಿ, number of ions ಹೆಚ್ಚಿಗೆ ಆಗತೈತಿ, conductivity will also increase. If you go on decreasing the concentration, number of ions will decrease. Simple. So conductivity also decreases. Now same thing we will see in a different way. Okay. That means ನೀವು concentration ಕಡಿಮೆ ಮಾಡಾಕತ್ತೀರಿ ಅಂದ್ರೆ ಅದರ ಅರ್ಥ ಏನು? You are putting the solvent. ಹೆಂಗ್ ಜಾಸ್ತಿ solvent ಹಾಕೊಂತ ಹೊಂಟಿದ್ದೀರಿ, correct? So you are putting more solvent. And what does that mean? It means we are talking about dilution. We are talking about dilution. Now I say I have increased dilution. Dilution ಹೆಚ್ಚಿಗೆ ಮಾಡಿದೀನಿ ಅಂತಂದ್ರೆ ಏನು? ಅಂದ್ರ I have put more solvent there. That means number of ions per unit volume is less now. Number of ions per unit volume is less. Yes or no? Number of ions on dilution per unit volume has decreased. Yes, number of ions are same. Ions badlagilla. Solute ನಾನು ಏನು ಡಿಸ್ಟರ್ಬ್ ಮಾಡಿಲ್ಲ. ಡೈಲ್ಯೂಷನ್ ಮಾಡಾಕತ್ತೀನಿ ಅಂದ್ರೆ ಐ ಆಮ್ ಪುಟಿಂಗ್ ಮೋರ್ ಸಾಲ್ವೆಂಟ್. ಸೊ ವಾಲ್ಯೂಮ್ ಜಾಸ್ತಿ ಆದಂಗ ಪರ್ ಯೂನಿಟ್ ವಾಲ್ಯೂಮ್ ಕನ್ಸಿಡರ್ ಮಾಡಿದಾಗ ಕಡಿಮೆ ಅಯಾನ್ಸ್ ಬರಾಕತ್ತು, ಜಾಸ್ತಿ ವಾಲ್ಯೂಮ್ ಒಳಗೆ ಹೋಗ್ಬಿಟ್ಟಾವ, ಈಗ ಅಯಾನ್ಸ್ ಡಿಸ್ಟ್ರಿಬ್ಯೂಟ್ ಆಗಿದಾವ. ಎಸ್, ಸೊ ನಂಬರ್ ಆಫ್ ಅಯಾನ್ಸ್ ಪರ್ ಯೂನಿಟ್ ವಾಲ್ಯೂಮ್ ಕಡಿಮೆ ಆಗೈತಂದ್ರ ಕಂಡಕ್ಟನ್ಸ್ ಡಿಪೆಂಡ್ಸ್ ಆನ್ ವಾಟ್, ಕಂಡಕ್ಟಿವಿಟಿ ಡಿಪೆಂಡ್ಸ್ ಆನ್ ವಾಟ್, conductivity depends on the number of ions per unit volume. So when this number of ions per unit volume has decreased, conductivity also decreases. Conductivity also decreases. Yes. So this is about the conductivity and molar conductivity. Now let us say you have molar conductivity case. Okay. Molar conductivity. So I am going to talk about variation of kappa in molar conductivity. Okay, molar conductivity. So let us understand the variation. Okay, variation in molar conductivity. Fine. Okay. So see, conductivity per unit molar concentration means in that solution we have taken 1 mole of a solute. Molar concentration andra 1 mole of solute, number of moles of solute dissolved in volume of solvent solution antira haudanilla. So we have taken 1 mole of solute here. So here this is very interesting. See, it's totally opposite. Enantadappa, increase the concentration, conductivity, or let me be more specific, you increase the concentration, molar conductivity decreases. You decrease the concentration, molar conductivity increases. Opposite. So here this is a very interesting fact. So understanding this becomes very important. So let's see how on increasing the concentration, molar conductivity decreases, and vice versa will be understood. So we will be talking about for both weak electrolytes and strong electrolytes. So with the dilution, what happens? Molar conductivity is increasing slowly. If I want to show you by graph, I'll tell you here. See, you can see here. If I say I have a plot of concentration versus molar concentration, this will be the graph for strong electrolyte, say KCl. This will be the graph for weak electrolyte, say CH3COH. So you can see, if you consider strong electrolyte, let us consider strong electrolyte. Okay, here Kohlrausch law comes into context. So as we have discussed earlier, molar conductivity lambda m is equal to what? It is kappa by C. Conductivity per unit volume. Heng define ಮಾಡ್ತೀರಾ ಅದನ್ನ? Conductivity per unit concentration. Correct? So conductivity per unit concentration is my molar conductivity. So please see carefully. What's this concentration? What is this concentration? C is what? C is number of moles of solute. Number of moles of solute by volume of solution in liters. Here we are talking about 1 molar solution. If I say 1 molar solution, my concentration C should be 1. So this I can write it as C is equal to 1 by V. Are you all getting? So molar conductance, I can write lambda m is equal to kappa into volume. Correct? So molar conductance is kappa into volume, because C is at the denominator. C 1 by C is V. Yes or no? So kappa into volume. This was what we had seen there. So this relation is very important when you're trying to understand the variation. Okay. So on dilution, concentration ಏನಾಗುತ್ತೆ ಹೇಳ್ರಿ? On dilution, concentration decreases. Yes. Dilution ಮಾಡೋದ್ರಿಂದ concentration decrease ಆಗಕತ್ತೈತಿ, but volume is increasing. Volume ಹೆಚ್ಚಿಗೆ ಆಗಕತ್ತೈತಿ ಯಾಕಂದ್ರೆ more amount of solute you are adding. So I can say molar conductivity, what will happen is K into V. On dilution, K is decreasing, V is increasing. One is molar conductivity is related to both the terms. One is kappa and one is volume. Two terms lindanu directly proportional aiti. But here K is decreasing, V is increasing. Correct? So who is my decision maker? Decision maker is volume. This is my decision maker. So if volume is increasing, lambda m will increase. Volume ಯಾವಾಗ increase ಆಗ್ತೈತಿ? Dilute ಮಾಡಿದಂಗ. So as dilution increases, molar conductivity increases. So as dilution increases, volume of the solution increases. As volume of the solution increases, molar conductivity also increases. As the dilution decreases, volume decreases, molar conductivity also decreases. And vice versa for concentration. Understanding? So this is about molar conductivity. Okay, this is about molar conductivity. Fine. So here, so they have taken a numerical. You can see here. I'll take second one, easy one. This is easy. You all will do it. I'll just discuss. I'll just tell you how it can be done. A 0.05 molar NaOH solution, resistance of 31.6 ohm in a conductivity cell at 298 Kelvin. If area of the plates of the conductivity A is given 3.8 cc, distance between them, area kotirtara, distance between them is 1.4 centimeter. Calculate molar conductivity of NaOH. So cell constant G is equal to what? G star L by A. How much is my L? Distance between them 1.4 centimeter. Divided by A is what? Area of cross section of the conductivity cell 3.8. Correct? 3.8. So given concentration is what? How much concentration is given? 0.05 molar. 0.05 molar concentration. Fine. Okay. So here resistance is given 31.6 ohm and temperature is also given, that is 298 Kelvin. So conductivity is what? Conductivity is kappa is equal to conductance into cell constant. So G star by R. So conductance, you have calculated this G star here. You have got this so much value. Substitute these values, you will get the answer. Molar conductance is what? 1000 into K by M. Lambda m is equal to, we have seen in our previous slide, 1000 into K into 1000 by M. 1000, the conversion factor, into how much is my kappa? I've got here 0.0166. Yes, divided by 0.05. Okay. Substitute, simplify, you will get this much answer. Similarly, you can take other numericals also. Okay. Now, so factors affecting we have seen. Molar variation of molar conductivity also we have seen. So molar conductivity with temperature. The increase of temperature ಹೆಚ್ಚಿಗೆ ಮಾಡಿದಂಗ interanic attractions ಏನದಾವಲ್ಲ, they will decrease in the solution of an electrolyte and increases the kinetic energy, that is speed ಹೆಚ್ಚಿಗೆ ಆಗುತ್ತಾ. Thus molar conductivity increases with increase in temperature. As you go on increasing the temperature, the molar conductivity increases. Okay. So here we are having a very important law, which is called Kohlrausch law. Kohlrausch law of independent migration of ions. So what Kohlrausch law says? Kohlrausch law says that the limiting molar conductivity Kohlrausch law. The limiting molar conductivity, which is denoted by lambda m naught. Limiting molar conductivity denoted by lambda m naught. So what is limiting molar conductivity? C tends to 0 adaga molar conductivity becomes limiting molar conductivity. Okay. When a concentration term tends to 0, andre ಒಂದು solvent na ಬಹಳ ಕಡಿಮೆ ಪ್ರಮಾಣದಲ್ಲಿ ತಗೊಂಡಾಗ C tends to 0. Concentration comes to 0. Concentration is decreasing, comes closer to 0. Means if we have diluted the solution infinitely, have added so much solvent, say solute has remained for namesake. So C tends to 0. When it tends to 0 at infinite dilution, when C tends to 0, then particular value of M is being obtained corresponding to 0. That is called limiting molar conductivity, denoted by lambda M naught. Limiting molar conductivity of an electrolyte can be represented as the sum of individual contributions of anion and cations of the electrolyte. Individual contributions of the anions and cations. Andre, so let me suppose we talk about NaCl electrolyte, and you know that NaCl dissociates into Na plus cation, Cl minus anion. So when I talk about limiting molar conductivity, it is limiting molar conductivity of Na plus ion plus sum of limiting molar conductivity of Cl minus ions, sum of the molar conductivities of both the ions. So if you are talking about an electrolyte in which, if I say I have these many number of positive ions and these many number of negative ions, these many number, so the psi number of psi positive ions and psi negative ions, then how much will be the total number of cations? Total number of cations will be psi plus into lambda naught plus total number of anions will be psi minus into lambda naught minus. Yes, so sum of this will be my limiting molar conductivity of an electrolyte. That will be equal to psi plus into lambda plus naught plus psi minus into lambda naught minus naught. Yes, so don't get confused. Limiting molar conductivity, alla ions molar limiting molar conductivity add madidra, you will get the limiting molar conductivity of the electrolyte. Okay, so let us consider a weak electrolyte here. Let's suppose say a CH3COH acetic acid, ethanoic acid. So initially in the beginning, it dissociates as CH3COO minus plus H plus. So if I say initially the concentration of CH3COH is C, then the concentration of these two will be 0, because initially Andre, you have just going to start the reaction. So much concentration you have taken. Okay, now after some time, what happens? It will dissociate partially. Yes, so I can write C1 minus alpha, and here how much dissociation? C alpha, this also C alpha. This will dissociate. Yes, alpha is degree of dissociation. I'll not go deep into this because you have already studied this part. Assuming that you know the things, I'm writing this. Since this is at equilibrium, I'll write equilibrium constant K, and that will be equal to what? It will be equal to concentrations of products C alpha into C alpha by concentration of the reactant 1 minus alpha. So this can be written as C square alpha square by C 1 minus alpha. 1C gets cancelled. So K is equal to what? K is equal to C alpha square by 1 minus alpha. Yes, that means concentration of the products by the reactants. So simplified, this value you get, where alpha is what? Degree of dissociation, C is concentration. So for weak dissociation of the weak electrolyte into its all ions, but here what we have to involve is molar conductivity. Yes, molar conductivity concept namu beku. Fine. So molar conductivity E naught M of, okay, let me say how to introduce molar conductivity. E naught M of calcium chloride, I'll give you example. Another example you consider is what? Limiting molar conductivity of Ca plus 2 ions plus limiting molar conductivity of Cl minus ions. look at the reaction first. CaCl2 dissociates into Ca plus 2 and Cl minus. Balancing the reaction, I get 2 here. Therefore, I'll write 2 into lambda naught m Cl minus. Psi minus number of Cl minus ions into its limiting molar conductivity. Number of Ca plus ions into its limiting molar conductivity. From the table, we know that limiting molar conductivity of Ca plus 2 is 119 plus 2 into limiting molar conductivity of Cl minus is 76.3. This you solve out, it comes out to be 271.6 Simons centimeter square per mole. Cleared with this? So this is how you solve the molar conductivities, limiting molar conductivities. You find the limiting molar conductivities. Okay. Now let us move on to the next concept. Which is our next concept? We are going to talk about application. Okay, fine. Applications of Kohlrausch law. Just now we have seen such example, right? Acetic acid, CH3CO minus acetate ion, H plus. So this is what you have seen just now. Fine. So here you can solve limiting molar conductivities are given. Calculate the molar conductivities are given. Calculate the limiting molar conductivities. It does not become much difficult, right? You can solve it like this. Fine. So here are some of the numericals for the practice. You can take it or you can put it in the chat box if you have not understood the concepts. Okay. Now we are going to talk about the electrolytic cells. Electrolytic cells. So these are the cells in which electrical energy is converted into mechanical energy. In the first session, we had said in this chapter, we are going to talk about two things. Using chemical energy, we are going to generate electricity. That is my electrochemical cells. Correct. So what was happening there? The spontaneous reactions in a Togonbitu, we were generating electricity in the electrochemical cells, galvanic cells, voltaic cells, Daniel cell we had seen as an example. Here, further, the second part, what we were talking about was using electricity, how we are going to bring about a reaction which is not going to occur on its own. A naughty student will not study on his own. A naughty child at home will not study on his own. So what external things we have to put? Either we have to shout that child, you'll study or no. I have to hate that child. I have to put an external push. If you don't study, I will not take you out. All these things, what they are the external push which is being given to the child so that he will study. Similarly, there are certain reactions which do not occur on their own. So to make those reactions occur, such reactions are called what? They are called non-spontaneous chemical reactions. So to bring about these non-spontaneous chemical reactions, you need to give an external push from the outside, external source. So what is that external source? Tell me. The external source is the voltage what we are going to apply. That is in the form of electricity, correct? So using electrical energy, I am going to bring about a chemical reaction which is not going to happen on its own. I am going to bring about a non-spontaneous chemical reaction, right? So here and that is going to take place where it is going to occur in a cell called electrolytic cells. So let us now understand electrolytic cells. Okay. So in the electrolytic cell, an external energy source of voltage, that is electrical energy, is used to bring about a non-spontaneous chemical reaction. Electrolysis is a process of what? It is process of breaking down of an electrolyte, decomposition of an electrolyte using electric current. So electrolysis, electro stands for electricity. Lysis stands for to break down. So you are breaking down what? You are breaking down an electrolyte. You are breaking down a compound into its ions. So decomposition is going to take place of the electrolyte in presence of electric current. When electric current is passed through it in solid form, no, not at all. Either in the solution state or in the molten state. Solution state andaga when you take it in water, either in the aqueous solution or in the molten state. Now in electrolytic cell also, we talk about oxidation and reduction. Okay. Unlike in electrochemical cell, we were having half cells, right? one side half cell oxidation half cell, another side reduction half cell. Oxidation hatra yavudu electrode, anode, reduction hatra cathode, and at anode there was loss of electrons, at cathode there was gain of electrons. All these things also we will be talking here in the electrolytic cells. We'll be talking here. Okay, so you can see here anode is positively charged where oxidation takes place, and cathode is negatively charged where reduction takes place in the electrolytic cell. So anode, oxidation, positive; cathode, reduction, negative. During electrolysis of molten electrolyte, cations are liberated at cathode while anions at the anode. So cathode is by negatively charged. Now the question is why cathode is negatively charged. Okay. Okay, let me take here. Cathode yak now negatively charged antidivi. Okay. So we are going to talk about the electrolytic cells now. So as I said, electrolytic cell andaga, it is only single cell in which both the electrodes are dipped. So let us understand the setup first. See, this is a container which you call it as a cell, and both the electrodes are dipped in the same solution. Both the electrodes are dipped in the same solution. Okay. So here I have used a battery. Unlike in electrochemical cell, we had not had a battery, right? Because chemical reaction was happening there. So here using this battery, you are going to potential na use madbitu. Now we are going to produce electricity and making the chemical reaction to occur, non-spontaneous chemical reaction to occur. Fine. So this is my cathode, which is connected to negative terminal of the battery. This is my anode, which is connected to positive terminal of the battery. Fine. So let us understand this electrolysis process. So see, we have two applications of this electrolysis. One is purification of copper, and second application is electroplating. So let me consider this purification of copper to understand the process of electrolysis. Okay, so let me say these both electrodes, what I've taken is both are copper electrodes. I have copper electrodes. Okay, fine. Okay, now what solution I have taken? The solution is its electrolyte only. The electrolyte what I choose should contain this ion. So I'll take copper sulfate solution. So I'll take copper sulfate solution. Fine. Okay. So cathode is connected to the negative terminal, anode is connected to the positive terminal. So since a negative charge is on the cathode, negative terminal, so what is flowing here? Electrons are flowing here. So since negative charge is on the cathode, in the solution I have Cu plus 2 ions and SO4 minus 2 ions, correct? Since negative charge is there on the cathode, the Cu plus 2 ions which are present in the solution, they will see those electrons, they become very happy, they will run towards the cathode, and they will take those electrons and go on depositing on this cathode. Getting understanding? So Cu plus 2 ions from the solution, they will move towards the cathode. There is gain of electrons. So what is gain of electrons? Reduction, red cat. So reduction is occurring at cathode. Fine. Now, since what is my anode made up of? My anode is Cu. Now see, Cu can lose electrons. Cu will lose electrons and become what? Cu will lose electrons and become Cu plus 2. So where that Cu plus 2 will come? By losing the electrons, Cu plus 2 is coming into the solution. Cu plus 2 is coming into the solution. So what's happening at cathode? Cu plus 2 from the solution is going on the cathode, gaining the electrons. Gain of electrons is reduction. And we always know that reduction, red cat. So reduction is occurring at cathode. Clear with this picture? Come back to anode. What is the story of anode? So at anode, copper will lose 2 electrons to form Cu plus 2. It will form Cu plus 2, and this Cu plus 2 will go into the solution. So what is the entire scenario of this process? Cu from anode is becoming plus 2 and coming. So anode atra oxidation agakatati, loss of electrons. So Cu from anode, at anode oxidation is taking place and at cathode reduction is taking place. Overall, if you see what is happening, the story is from anode Cu is coming into the solution and becoming Cu plus, and that Cu plus itself is going on to the cathode, taking the electrons and getting deposited as Cu on the cathode. In a simple words, if I want to say Cu from anode is getting out, coming into the solution, and in the cathode Cu is getting deposited from the solution. So you can show this Cu from anode is coming into solution. Heng barakatitadu in the form of Cu plus 2. And this Cu plus 2 from the solution, it is going and depositing on cathode. In what condition it is going? It is going like this Cu, because it is taking 2 electrons and getting deposited as Cu. Yes. So what we do here during purification, this is electrolysis process. So during purification of copper, I have a impure rod. I'll take it as anode. So yenagtati. So idral irtakanta Cu, it will lose electrons and come into the solution. So Cu2 plus ag baratte. That Cu plus 2 will go take the electrons from cathode and go on depositing on the cathode. So after some time, if you see, illi anode alli irtakanta copper ashte, only copper. Lest all things won't come. Only copper is getting out into the solution and it is in turn going and depositing on cathode. So cathode rod, after some time, it will go on becoming thick and thick. So you can see the deposition of copper on cathode rod. Okay, same thing is seen in electroplating also. Electroplating alli enagutte hedri, I will take same electrolytic cell. As anode, I'll take, see, yaudan toltiri. For example, electroplating alli you have heard so many things. What all you have heard? You have heard about gold plating, gold plated ornaments ಬಗ್ಗೆ ನೋಡಿವಿ. Gold plated ornaments we have seen. Then we have seen silver plated articles. Silver plated articles pooja ki use ಮಾಡ್ಲಿಕ್ಕೆ ನಾವು ನೋಡಿದೀವಿ. Then we have seen chrome plated handles, bathroom all the things whatever we'll be using, handles we have seen. So if I want a plating of one metal on another object, then that using electricity, if I do it, it is called electroplating. So I want gold let me say I have a I have a vessel, and to that vessel, that is a vessel of steel, I have a steel vessel. Adak horaginda I want plating of copper. So copper plated vessels we use. Copper plated plates are there, copper plated glasses are there, copper plated utensils are there. Yes, so copper plated utensil nanag madodaitappa. I want to do copper plated utensil. So what I will do? So I will take the particular object which I want to have a coating on it. That particular object I'll take it as cathode, because I know anode linda metal bandbittu solution ಅಲ್ಲಿ ಬರ್ತೈತಿ, solution linda ಹೋಗಿ ಅದು cathode ಮೇಲೆ deposit ಆಗ್ಲಿಕ್ಕತ್ತದ, correct? And as anode what I'll take? ಯಾವ element the plating ಬೇಕು, that element I'll take. Now I want copper plated utensil. So nanu as an anode I will take copper. So this is my anode. Connect it to a battery. Negative terminal, positive terminal. Now what solution you take? The solution of this particular metal. Electrolytic solution of this particular metal. So copper aiti. So I'll take copper sulfate. Imagine another situation. I have an ornament. Other mel nana gold plating madodi. So I will take ornament as cathode and gold as anode. Au as anode. So Au the solution, I'll take it as the electrolyte. Are you all getting? So when you pass the current, when potential is applied, what happens? Copper, consider this itself, copper plated utensil. Copper from the anode will lose electrons. It will come into solution as Cu plus 2, and this Cu plus 2 will see the electrons here because electron flow iti, will go and take the electrons. That means it will go on depositing on the It will go on depositing on the cathode, on the article which is placed on the cathode. Getting? So this is about electrolysis. Okay. So when two or more ions compete at electrodes, the ion with higher reduction potential gets liberated at cathode, while the ion with lower reduction potential gets liberated at anode. Yes. So you understood the concept of electrolysis. Now the question is, before we go to how to predict the products of electrolysis, what is the question is how to quantify this electrolysis, meaning how to make it measurable. How much amount of metal is getting deposited on cathode? Adanna heg measure madodu? How do you measure? How do you quantify the electrolysis? Yes, any metal is going on depositing on cathode. Okay, but how much copper will get deposited? Copper plated bekappa. How much copper? Yes, what are the factors on which we can say how much copper will deposit? Factors irbekala. Yes, so these questions, to answer these questions, a scientist by name Michael Faraday, he had given some laws. He has given two laws. So they are first and second laws, which answer this question. In fact, Michael Faraday was the first scientist who described the quantitative aspects of electrolysis through his two laws. He described the quantitative aspects. So now let us see Michael Faraday's first law. Yes, what does Michael Faraday's first law says? Okay, fine. Let us see here. Faraday's first law. So what does this first law says? The amount of chemical reaction, which occurs at any electrode, when during electrolysis by current. Idhan mention mado avashyakate illa, because electrolysis andre you are using current, is directly proportional to the quantity of current or quantity of electricity passed through the electrolyte. This is Faraday's first law. What does that mean? If I say I have electrode, what we have dipped in the electrolyte. Now, how much chemical reaction occurs? How much? What does that mean? How much copper from anode is going to get deposited on the cathode? How much copper is going to get deposited? It is dependent on what? It is dependent on how much electricity you are passing. Through that particular electrolyte. Battery aithe potential you are applying. So ಎಷ್ಟು electricity pass ಮಾಡ್ತೀರಿ, on that basis the amount of copper getting deposited on the cathode is based. So if you take the example of copper plating setup, if I have pass very less amount of current, then only little amount of copper gets deposited on it, right? But if I pass more amount of current, or you can say current for a longer time, understanding, if I pass current for a long time, more copper will get deposited on the cathode. Okay, so basically it's depending on two things, that is how much current you have passed, and for how long. Andre the amount of time, it is dependent amount of current, it is dependent on amount of current, and it is also dependent on time. So I can say the amount of substance depositing, if I denote it by W, amount of metal getting deposited on cathode, it is directly proportional to Q. What is Q? It is charge. And you know that what is charge? Charge means what? I know Q is equal to current into time. You know this expression, physics, Q is equal to IT, right? So W is equal to what? W is directly proportional to I into T. So what is W? Weight of the component getting deposited on cathode. Weight of the component getting deposited on cathode. So this is my Faraday's first law. Now let me say, what is Faraday's second law? What is Faraday's second law? Fine. Okay. Now let's suppose instead of one, I have two containers. Let's suppose that I have two containers. In first container, I have two electrodes, cathode ಮತ್ತು anode. This is anode, this is cathode. So battery is there. Fine. Let me say this is silver electrodes. Both are silver electrodes dipped in silver nitrate solution, its own electrolyte. And this is, I have in the other one, I have taken, let me say, plus and minus. So this is anode, this is cathode. Here, let me say both the electrodes are copper. Both the electrodes are copper. So I have taken copper sulfate solution. Okay. So both the electrodes, they are again, rather than saying connected here, connectivity, rather than showing connectivity like this, let me say they are both connected to single potential. Plus and minus. Fine. Okay. But will that mean both sides, same amount of, on both the cathodes, same amount of element gets deposited? That is on silver cathode, silver, same amount of silver gets deposited, and here copper cathode, same amount of copper gets deposited? Absolutely not. Even though same amount of electricity is being passed at two different metals, both Cu and Ag, both are different metals, right? Properties of both the metals are different. Tendency of both the metals towards the reactivity is different. Reacting speed is different. Nature is different. Property is different. Everything is different. Then how can you expect same amount of element getting deposited on the cathode? Understanding? So they are different metals. We cannot expect the same quantity for both. So on this basis, Faraday's second law comes into context. So when you have two different cells in which you have taken two different solutions, the amount of, it says, the amount of different substances liberated by same quantity of current. Same quantity of current or same quantity of electricity passing through the electrolytic solutions are proportional to their chemical equivalent weights. Chemical equivalent weights. The amount of different substances liberated by same quantity of current, electricity, passing through the electrolytic solutions are proportional to their chemical equivalent weights. Means how much copper or how much silver is getting deposited on the cathode will depend on their equivalent weight. So let's say copper, the equivalent weight is how much? Let's say copper. So let me take first copper. Copper is depositing W1. Okay. So W2 I'll take with respect to silver. So W1 is with respect how much amount of copper is deposited, and Ag, for Ag I'll take it as W2 getting deposited. So W1 by W2 is equal to E1 by E2. Equivalent weights of copper and equivalent weight of, ratio of equivalent weight of copper and equivalent weight of Ag, or in general, I can say equivalent weight of element 1, metal 1 and metal 2. So what question arises here? What's equivalent weight? We have already studied. What is equivalent weight? Equivalent weight is nothing but It is the atomic weight divided by valency factor. Now, what is this valency factor? Valency factor is nothing but the number of electrons accepted by metal ion is valency factor. Example, Zn plus 2 I have. Zn plus 2 will accept how many electrons? It will take 2 electrons to form Zn. So what is the valency factor of Zn plus 2? Valency factor of Zn plus 2 is 2. Yes. Similarly, take example of Al plus 3. I have Al plus 3. It will take how many electrons? It will take 3 electrons to form Al. So what is the valency factor for Al? It is 3. Here it is 2. If you take lithium plus 1, it will take 1 electron and forms lithium metal. So what is the valency factor for lithium? It is 1. So this is valency factor, equivalent weight, atomic weight divided by valency factor. Okay. So from the first law, Faraday's first law, how much mass gets deposited on cathode? How much mass gets deposited on cathode? Now I know W is directly proportional to Q. And what is my Q? Q is I into T. Okay. So if I say for 10 minutes, if I give you example, T is 10 minutes and I is 1.5 ampere. So what will be my Q? Q will be 1.5 into 10 minutes has to be converted to seconds. So 10 into 60, that is equal to 600 seconds. So into 600. So how much I'll get? I'll get this as 900 coulombs. Correct? So if I take an example of a reaction where CuSO4 is there and Cu is getting deposited. So Cu is in what state? Cu is in +2 state. So it will take 2 electrons and form Cu. Correct? Fine, solid Cu. How much charge will I need? The question is how much charge will I need? Here I say I need 2 Faraday of charge. 2 Faraday of charge, that is electricity. So I can say on passing 2 Faraday of electricity, 1 mole of copper is getting deposited. But how much charge I have? I have 900 coulombs of charge. So 900 coulombs of charge idaga, how much copper gets deposited? So 1 by 2F into 900. So how much is the value? 2 into 96487 into 900. When you solve it out, this much moles of Cu will be deposited and the answer bartade. Okay. So moles of Cu is there. This much moles. Number of moles. See, what is number of moles? Given mass upon molar mass. Therefore, if I want to find the mass amount of copper deposited, M is equal to what? Number of moles into molar mass. Illi niಮಗೆ number of moles answer ಸಿಕ್ಕಿರುತ್ತೆ into molar mass of copper. You put it, you will get the mass of copper deposited on the particular cathode electrode. Yes. Now we need to understand the products of electrolysis. How to predict the products? Yes. On what factors electrolytic products depend? That is very important. So nature of the material being electrolyzed. Nature of the material being electrolyzed. So nature of the material being electrolyzed andre, which things are getting electrolyzed? What is their nature? I mean, in electrolytic cell, what all things are there? What's their reducing power? What's their oxidizing power? What's the electrode potential of the electrodes? Reduction potential, oxidation potential, right? The second factor on which it depends is the type of the electrode being used. Electrodes also can be inert, non-reactive electrodes which do not react, do not participate in the reaction, like my platinum electrode which we have used in She, right? So there might be electrodes which are reactive also, which themselves also react depending on my electrolyte. So depending on my electrode which is inert or reactive, also the products of the electrolysis depend. And the third one is kinetics of the reaction. Kinetics of the reaction means the speed of the reactions. Sometimes we have some reactions like which are feasible, which will occur, but which are possible, we can say, but they will happen very, very, very slow, almost equal to not happening. Such slow reactions, in case of such slow reactions, we need to put extra energy, extra potential, extra push from outside, for which we call overpotential. We call overpotential. So these are the factors on which the products of the electrolysis depend. And how to predict it? So when aqueous solutions of electrolytes are electrolyzed, if cation has higher reduction potential than water, cation is liberated at cathode. Yes. So in the electrolysis of copper and silver salts, standard reduction potential Cu plus 2 bar Cu and Ag plus bar Ag, it is 0.34 and 0.20. Otherwise, H2 gas is liberated due to reduction of water. Okay. Similarly, if anion is having higher oxidation potential than water, this you might have recalled. We have seen in one of the examples when we talking about E cell and all. Yes, more stable ion will be formed. It will not allow to go into that particular state itself. Reduction reduction agudela when we're discussing reduction potentials. We have discussed there. Okay. So in case of oxidation potential, O2 gas is liberated due to oxidation of water. Yes. For metals to be deposited on cathode during electrolysis, the voltage required is almost same as a standard electrode potential. So for a metal to be deposited on cathode, how much voltage is required? It is almost same as standard electrode potential. However, for the liberation of gases, some extra voltage is required than the theoretical value of standard reduction potential. This extra voltage is called what? This extra voltage, you need to put an extra external push kodbekagutte. That extra voltage is called what? Over potential. When we talk about kinetics of the reactions, when the reactions are not are happening, they are feasible, they are happening, but they are happening in such a situation, such a condition, like it is almost equal to they are not happening. So slow the reaction is proceeding. If the reaction is so slow, what we do? We give some extra potential than the normal potential. Normal potential we are applying. ಅದಕ್ಕೂ ಮೀರಿನೂ ನಾವು ಏನ್ ಮಾಡ್ತೀವಿ? ಇನ್ನೊಂಚೂರು ಜಾಸ್ತಿ potential ಕೊಡ್ತೀವಿ. So that extra potential is called what? It is called over voltage or bubble voltage or over potential. Fine. So products formed during the electrolysis of brine solution, electrolysis of molten NaCl using graphite electrodes, inert electrode we have taken. So in the molten state, NaCl dissociates as Na plus and Cl minus. And you know that cathode hatra ಏನು ಹೋಗುತ್ತೆ? Cathode electricity minus negative terminal ಇದೆ. So electrons are there. So Na plus will go at cathode. ಅಲ್ಲಿ ಏನ್ ಮಾಡ್ತೈತಿ Na plus? Na plus will take those electrons. When Na plus takes that electrons, there is gain of electrons. Gain of reduction electrons means reduction, which is happening at the negative electrode and forms Na. And at anode, what happens? Cl minus, my negative ion will go at anode, because anode is positive, connected to positive terminal of the battery. So early Cl minus will lose the electrons and it will form Cl2. So overall reaction during electrolysis, NaCl, when it is subjected for electrolysis, you get Na at cathode and Cl2 gas at anode. So using graphite electrodes, you can see here, standard reduction potential Cl2 bar Cl minus is 1.36, which is less than water. So water should be liberated, oxygen should be liberated at anode. But dissociation of H2O into O2 is kinetically very, very, very slow. It is feasible, but it is extremely slow. So to enhance the rate, extra potential is applied, which you call it as over potential or over voltage. This oxidation potential of Cl minus bar Cl2 is achieved. The Cl2 is preferentially produces at anode in place of O2. So this Na plus, it combines with OH and forms NaOH. Therefore, pH of the solution increases after the electrolysis. So you can say NaCl na aqueous solution of NaCl is called brine solution. NaCl na ನೀವು electrolyze ಮಾಡಿದಾಗ, when you subjected for electrolysis, NaCl decomposition ಆಗುತ್ತೆ. Na plus Cl minus, all that we have seen. Na plus cathode reaction ನೋಡಿದ್ವಿ, anode reaction ನೋಡಿದ್ವಿ. So overall products are NaOH. That's the reason pH of the solution increases. And then we have H2 and Cl2 gases liberated. So this is for this session. In the next session, we will move to the next concepts of electrochemistry, and preferably that will be the last session for electrochemistry. Hope you have understood the concepts. We will be using the same things while solving the multiple numericals and while solving the competitive questions. Yes, for now, thank you.